Good morning. This is a review of Exam 2 for Math 1060, and we'll go ahead and get started. The first thing we want to do is look at some formulas that you'll need to know before the exam. First being the even-odd identities, and hopefully you remember these. The first even-odd identity we have here is sine of negative x equals negative sine of x, and if you remember, the sine is an odd function symmetric about the origin. So that's from where we can remember the even-odd identities. And then we have the cosine, which is an even function, which gives us that the cosine of negative x is equal to the cosine of x. Additionally, the tangent is an odd function, which gives us that the tangent of negative x equals negative the tangent of x. For the other three trigonometric functions, they follow along with this. From the sine being an odd function, we have the cosecant also having an odd identity. The secant follows the cosine in being an even function, and the cotangent follows the tangent in being an odd function. So altogether, we only have two even functions, that the cosine and the secant. Okay, so an example of a problem that we might solve using the even-odd identities is, say we want to simplify. Oh, I can't write good yet today, so let's see. It is early when I'm recording this. Let's simplify the identity sine of negative x times the secant of negative x all over the cotangent of negative x. So we've got a few different functions in here. Okay, so the first thing I do in simplifying this is the sine being an odd identity would give us, we could write the sine of negative x as negative the sine of x. And then the secant being an even function, we could write secant of negative x as secant of x. Just get rid of the negative altogether. The cotangent of negative x is, we can write that as a negative cotangent of x, being that the cotangent is an odd function. And then we have a negative divided by a negative would give us a resulting positive fraction here, and we'll just simplify a bit further. I have the sine of x times the secant of x, which is 1 over the cosine, and then the cotangent of x, which would be cosine of x over sine of x. And so what have we got? We've got, in the numerator here, we have sine of x over cosine x divided by cosine of x over sine of x, which would be the same as multiplying by sine x over cosine x. We end up with sine squared x over cosine squared x. And that simplifies to simply give us that tangent squared of x. Okay, well, moving on. Other identities you will need to know, and I would say maybe the most important for this particular content, is the sum and difference identities, in particular for the sine and cosine, since of course we could get that sum and difference identities for the tangent from those for the sine and cosine, starting with the sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. If we just flip that sign and make this sine of alpha minus beta, our sign here in the middle flips from a plus to a minus. And then we have the cosine of alpha plus beta equals, if you remember this, how I've kind of talked about it in class, the sine is a sharing function. It shares its first position here with the cosine, so we let it keep its plus sign. So we have sine alpha cosine beta plus cosine alpha sine beta. And same with, if we have minus here, sine alpha minus beta, we keep the minus. With cosine of alpha plus beta, the cosine doesn't like to share, so we make it change from a plus to a minus here. And then we have cosine alpha cosine beta minus sine alpha sine beta. And then if we just flip the plus to a minus and we look at cosine of alpha minus beta, we have cosine alpha, cosine beta, and then we flip this minus to a plus here. So we're going to have plus sine alpha, sine beta. However you remember these, it's something, I would say probably one of the more important identities that you need to have memorized for this class. And then we look at double angle identities, which actually come from the sum identities. If you remember what we were just looking at, the sine of alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. If we replace all the alphas and betas with theta, and in other words, we're only looking at one angle now instead of two, we have sine alpha cosine, we have sine theta cosine theta plus cosine theta sine theta. And then just putting that all together and condensing, this is the same as sine of 2 theta equals 2 sine theta cosine theta. With cosine of alpha plus beta, again, we'll replace all our alphas and betas with the angle theta. And now we have cosine of theta plus theta is equal to cosine theta minus sine theta. And simplifying gives us cosine of 2 theta equals cosine squared theta minus sine squared theta. And these are the results that I don't necessarily have these memorized or think that you have to. If you just remember to start with the sum identities and replace the alphas and the betas with the same angle of theta or whatever you want to use. Okay, so moving on. We want to do a little more with double angle identities before we start solving problems here. Remember your Pythagorean identity, sine squared theta plus cosine squared theta equals 1. And we can go back to the formula for cosine of 2 theta, which is cosine squared theta minus sine squared theta. And we'll start by replacing sine squared here with 1 minus cosine squared theta coming from the Pythagorean identity. And simplifying gives us that the cosine of 2 theta is equal to 2 cosine squared theta minus 1. So at this point, we have two different identities for the cosine of 2 theta. We can get one more if we go back to the original formula for cosine of 2 theta. And this time, using the Pythagorean identity, we replace cosine squared theta with 1 minus sine squared theta. And simplify to get the cosine of 2 theta is equal to 1 minus 2 sine squared theta. So putting those all together, we have three different identities for the cosine of 2 theta. And you'll want to make sure that you know all three of these, because depending on what problem you're trying to solve, sometimes it's really handy to substitute using totally cosine or totally sine. Although I generally would go with this original identity as long as it's not too hard to find the cosine and the sine of an angle. Okay, so let's go on. Half angle formulas. Again, these are formulas you basically just have to memorize, but it's good to know. The sine of theta over 2 is equal to plus or minus square root of 1 minus cosine theta over 2. The cosine of theta over 2 is equal to plus or minus the square root of 1 plus cosine theta over 2. These formulas are identical, so if you remember one, you should be able to remember the other. And the only difference is that we have a minus for the sine, we have a plus for the cosine. And I kind of remember that because we're going from cosine to cosine here, so we keep the plus, if that makes any sense. Anyway, make sure you know the half angle formulas as well for this exam. And other than that, the inverse trigonometric domain restrictions, when we're working with inverse trigonometric functions, are good to know. We have a little trick that I think we learned that might help some of you with this. In fact, I've noticed that most of you use this little trick. If we think of the unit circle, and right here we start with the sine of x, so this would be y equals sine x. And if we look at the domain restriction on the unit circle, and I'm just going to draw that part of the unit circle, our domain restriction is from negative pi halves to pi halves. So if we just sketch that part of our unit circle, this is where you're going to be looking in quadrant 1 or quadrant 4 when you're working with the arc sine. And if you notice, if we move on down, here we have the tangent of x. We have basically the same domain restriction, so we could repeat this. The only exception would be that we'd be missing these endpoints because the endpoints wouldn't exist here. And if we move on down to where we have y equals the cosecant of x, same domain restrictions except we're missing 0 here. So if we drew our little half unit circle, we'd be missing the point that falls along the x-axis here, going from the sine of x. So our domain restriction would go something like that. Okay, moving over to the cosine then. Here we have y equals cosine x. Our domain restriction goes from 0 to pi, so that looks a little bit differently. If we draw a half unit circle, it's going to be like so, from 0 to pi, and these are the two quadrants that you're going to be using when you're working with inverse cosine functions for the domain restriction. If we move on down to y equals the cotangent of x, notice we basically have the same domain restriction as the cosine. The difference would be that we'd be missing these endpoints here. So if I wanted to sketch my half unit circle, I'd need to exclude the points that fall on the positive and negative x-axes there. And then last of all, here we have y equals the secant of x. And so again, we need to start with the half unit circle from the cosine, but we're going to exclude the point that falls on the y-axis there, because at that point we would have a vertical asymptote going on for the secant, right? Okay, so this hopefully helps you with the domain restrictions, and let's solve some problems. The first problem I want to solve here is to find an equivalent expression for the tangent of the arc sine of x. Well, anytime I see an arc sine or an arc cosine, any inverse trigonometric function, I'm going to refer to that as theta, because what we're really talking about here is an angle. So I'm going to call the arc sine theta here, which means that if theta equals the arc sine of x, and note that we could call this sine inverse too. Basically, they're just different ways of saying the same thing. If theta equals the arc sine of x, that tells me that the sine of theta is going to equal x. From there, well, I don't know too much more about theta or about the arc sine of x, but I do know that the sine of theta equals x, or that the sine of theta is equal to x over 1. I can sketch a little reference triangle here to help me figure out what the tangent of theta would be, which if I can actually find the tangent of theta, I've solved the problem, right? So if I want to find the tangent of theta, I'll use a reference triangle, little right triangle here, where say this would be my angle theta. Then the sine of theta is equal to opposite over hypotenuse. I have a missing side here that I want to solve for. So I note that using the Pythagorean theorem, my missing side squared plus x squared equals 1 squared. So my missing side squared, remember we're solving for m, not for x here. My missing side squared is going to equal 1 minus x squared. So my missing side would have a length of square root of 1 minus x squared. Okay, we're almost done. All we're trying to find here is an equivalent expression for the tangent of the arc sine of x, which since we've renamed arc sine of x as theta, we're trying to find the tangent of theta. And if we look down here at this right triangle, the tangent would be opposite over adjacent, or x over square root of 1 minus x squared. Okay, and we got it. That's our solution for this first problem. All right, let's move on to number 2 here. Here we're finding the arc cosine of the cosine of 245 degrees. Okay, so the cosine of 245 degrees, well, let's see, where is 245 degrees at? It's going to be bigger than 180 degrees and less than 270 degrees, so somewhere here in the third quadrant. would be my 245 degrees. Let's see if we can figure out what the reference angle here is. Well, to find the reference angle, I'd do what? I'd take 245 degrees minus 180 degrees, and that would give 65 degrees, it looks like. So we have a reference angle of 65 degrees. If I'm trying to find the arc cosine of the cosine of 245 degrees, I need to be in the quadrant, and this is going to be a negative value here. So in quadrant 3, the cosine is negative. Okay, so if the cosine is negative, if I'm finding the arc cosine and I have a negative angle, I want to restrict my angle to the correct quadrant here, which in this case would be quadrant 2. And you can look back here where we had our little cosine. So for the cosine, we're either in quadrant 1 when we're working with inverse cosines, or we're in quadrant 2. For positive values in quadrant 1, for negative values in quadrant 2. This time we have a negative value for the cosine, and so we need to just move our angle up to quadrant 2. Well, the way I would do this, in quadrant 2, I'm going to put my reference angle of 65 degrees right here. And then I figure out what the resulting angle would be right here. To find this resulting angle, I would take 180 degrees minus 65 degrees, and I'd get what, 115 degrees, it looks like. So the arc cosine of the cosine of 245 degrees would be 115 degrees. All right, let's move on. Number 3, we're finding the sine of the arc cosine of negative 1/2. And when my arc cosine is in the argument, I'm going to give it the name theta. It's an angle. And so if I'm finding if the arc cosine of negative 1/2 is equal to theta, that means that the cosine of theta is equal to negative 1/2. Okay, so I'm finding the sine of the arc cosine of negative 1/2, where the cosine of theta equals 1/2. If the cosine, or I'm sorry, equals, it looks like I wrote 1/2 there. Okay, that happens sometimes. Those negatives kind of run into the fraction bar. So let's move that negative out front. So if the cosine is equal to negative 1/2, like we just talked about, the arc cosine, we're going to restrict our quadrant here to be in quadrant 2, where the arc cosine is, where the domain is restricted to for the inverse cosine function. And so if the cosine of theta equals negative 1/2, when we're in quadrant 2, let's see what angle that is. So in quadrant 2, the cosine is negative 1/2. Remember, we would have a reference angle of pi thirds, and so that would give us an angle theta of 2 pi thirds. Okay, so we end up looking back at our original function. The sine of the arc cosine of negative 1/2 is equal to the sine of 2 pi thirds. And hopefully you remember the sine of 2 pi thirds. We're in quadrant 2, where the sine is positive. Our reference angle is pi thirds. The sine of pi thirds is square root of 3 over 2. So this would be our final answer. The square root of 3 over 2 is the sine. If we're looking for the sine of the arc cosine of negative 1/2, it would be plus square root of 3 over 2. Okay, for number 4, we're finding the exact solutions in radians on the interval from 0 to 2 pi that satisfy this equation, secant squared x equals 4/3. Okay, so for secant squared x to equal 4/3, the first thing I'm going to do is I'm going to think of that would be the same as saying the secant of x would equal plus or minus the square root of 4/3. and that would be plus or minus the square root of 4, which is 2 over square root 3. Okay, and then I'm going to change that secant into a cosine. If the secant of x equals plus or minus 2 over square root 3, the cosine of x would equal plus or minus square root of 3 over 2, and hopefully that's looking a little more familiar. Well, if we're looking in the interval from 0 to 2 pi, then where is a cosine equal to either plus or minus square root of 3 over 2? And in quadrant 1, the cosine would be positive there. So here we would have a reference angle of pi over 6. In quadrant 2, the cosine is negative. We'd have a reference angle of pi over 6 there as well, as we would in quadrant 3 and quadrant 4. So we have actually an angle in each of our 4 quadrants that is a solution here, and with a reference angle of pi over 6, our x values would be pi over 6. Right here, pi over 6, we'd have what? 5 pi over 6 here. In the third quadrant, we would have 7 pi over 6. And then in that fourth quadrant, we would have 11 pi over 6. All right, and these would be our solutions on the interval from 0 to 2 pi. All righty, moving on. Number 5, we have a proof here, and I believe I've written this proof out so we can kind of just look at the solutions here. So we're going to prove the cosine of 3 theta equals 2 cosine cubed theta minus cosine theta minus 2 sine squared theta cosine theta. And where we usually have the rule to start with the more complicated side, I would say here, if we have cosine of 3 theta, I would start on that left side here. And the first thing we do is write down what the left side is. That's the very first step to getting the correct answer here. If you don't actually write down one side of your equation to start with, you'll get points off. So we have cosine of 3 theta, and starting with that left-hand side, I'm going to write that as a cosine of 2 theta plus theta, so that I can use a sum identity to break up the cosine of 3 theta. Using that sum identity, if we think of this as the cosine of alpha plus beta, we'd have cosine alpha cosine beta minus sine alpha sine beta, where alpha is 2 theta and beta is theta. And then we need to break that up a little more. So cosine of 2 theta, if you know your double angle identities, the cosine of 2 theta is one of the double angle identities is we write cosine of 2 theta as 2 cosine squared theta minus 1. And then over here, and where I probably got that is I probably am cheating a little bit looking up here at what I've got in my original equation that I'm trying to show. I'm trying to show that what I have on the left-hand side is equal to that right side. So I can see I have a 2 cosine cubed theta. It doesn't hurt to look at the other side of your equation. Just don't write it down until you know you've got the problem completed. And then for sine of 2 theta, there's only one choice for sine of 2 theta. So I'm going to replace that with 2 sine theta cosine theta. And then we'll simplify. We'll distribute the cosine of theta through to the cosine, 2 cosine squared into the 1. And we'll just simplify sine theta times sine theta. So we have 2 cosine cubed theta minus cosine theta minus 2 sine squared theta cosine theta. And are we there yet? Oh, we are. We're done. So we got it. This is actually the right-hand side. So we started with the left-hand side of the equation here. We ended up with the right-hand side of the equation. And we're done. Okay, now we have number 6, where we're going to find the exact value in radians of the cosine inverse of negative square root 3 over 2. So remember, this is an angle. Let's give it the name theta. From giving my cosine inverse an angle name, we can rewrite the equation in its other form as the cosine of theta equals negative square root 3 over 2. And here I'm finding the exact value. what quadrant are we in? And it seems like we have a lot of cosines today, but for the cosine of theta for it to be negative, we're going to, and when we're working with the inverse cosine function, we're always in quadrant 2. So we're looking for what value of theta in quadrant 2 would give me a cosine of negative square root 3 over 2. So let's see, we'd be about right here. And so we're going to have a reference angle of pi 6, which means that theta here would be equal to 5 pi over 6. And 5 pi over 6 is what we get for the cosine inverse of negative square root 3 over 2. Okay, and again, you could have used your little half circle, remembering for the cosine, the half circle that we're interested in, the half unit circle is like so. Okay, moving on, number 7. Find the exact value in radians of the arc cotangent of square root of 3. Again, I'm going to call this thing theta. And that tells me that the cotangent of theta, the cotangent of theta equals square root 3. Okay, what quadrant are we in for the cotangent of theta be square root of 3? This is what's kind of nice. Whenever we have positive values, we're always looking at quadrant 1. Okay, for any of these trigonometric functions. So in quadrant 1, we're looking for what angle gives me a cotangent of square root of 3. Okay, I made some notes before I started this, and I think I have the wrong answer in my notes. So hopefully I get the right answer here. I might double check this. So we're in quadrant 1. We have a cotangent theta equals to square root 3. Let's flip that into a tangent. The tangent would be 1 over square root 3. We're just a little bit more familiar with those tangent values, and we want to make sure we're in quadrant 1. For the tangent to be 1 over square root 3, we're going to have theta in quadrant 1 being equal to pi over 6. Okay, so this is the arc cotangent of square root of 3 is pi over 6. Okay, so let's go on. Our next problem is to find the exact value in radians. And I'm changing my notes here real quick on that last one. Find the exact value in radians of the tangent of sine inverse of 2/3. Okay, so once again, we have a sine inverse function this time. So I'm going to give that sine inverse the name theta. It's an angle. And now we're finding the tangent of theta. So if I find the tangent of theta, I'm done. Well, if we're looking at the sine inverse of the positive number, 2/3, then I can write that as sine theta equals 2/3. And I make a note. I always make a note what quadrant I'm in. I'm going to be in quadrant 1 because everything's positive here. But what our problem is here, we're looking for the angle theta that gets us a sine of 2/3 in quadrant 1. The problem is, I don't know what angle that would be. So what we need to do is sketch a little reference triangle here in quadrant 1. And I don't pay too much attention to dimensions here. So we just have a triangle, and whatever its side lengths are probably nowhere near what they should be, but the sine is equal to 2 over 3, opposite over hypotenuse. We need to find this missing side here. To find the missing side, we see that the missing side squared plus 2 squared equals 3 squared using the Pythagorean theorem. And so the missing side squared would be 9 minus 4, or 5. The missing side there is going to be positive square root 5 because we're looking at side lengths. Okay, so we don't need to worry about the plus or minus. So now all I need to do is find the tangent of theta. The tangent of theta is equal to the opposite over the adjacent, which would be 2 over square root 5, you can leave your answer like this. You can, if you want to, rationalize denominators. If we did want to rationalize this denominator, we would just multiply by square root 5 over square root 5. We'd end up with 2 square root 5 over 5. Either of these is a correct answer. All right, moving on. Number 9 here. We have the sine of theta equals a negative 3/5, where pi is less than theta is less than 3 pi over 2. So in other words, we're in what, quadrant 3, it looks like. Okay, so we're in quadrant 3. We're finding the cosine of theta. So once again, if the sine of theta is equal to negative 3/5, and we're in quadrant 3, so we're in quadrant 3 with a sine of negative 3/5. That's not a trigonometric function value that I know the angle for. So I'm going to go and make a reference triangle here in quadrant 3. And for this reference triangle, I know that the sine of theta equals negative 3/5. So the sine for my reference triangle is 3 over 5, opposite over hypotenuse. We need to find that missing side. Well, I could use the Pythagorean theorem, but seeing that the hypotenuse is 5 and that I have one side length of 3, I would know that this other side length is 4. And you can check that out if you want to. So to find the cosine of this angle theta, the cosine of my angle theta would be, it would be negative in quadrant 3, and it would be adjacent over hypotenuse. So we would end up with the cosine of theta is negative 4/5. Okay, and we have one more part to this problem. We want to find the cosine of 2 theta. So the cosine of 2 theta we can use any of the double angle identities we want. In fact, here we happen to know the sine and cosine. Well, I'll just use the original double angle identity for the cosine, which is cosine squared theta minus sine squared theta. The cosine of theta here is negative 4/5. The sine is negative 3/5. We end up with 16 over 25 minus 9 over 25, and that would give us 7 over 25. Alrighty, so we got it. 7 over 25 gives us the cosine of 2 theta. Now we want to find all real numbers that satisfy the equation cosine of 3x equals negative 1/2. It may also be stated, find the general solution to the equation. But if you're just told to solve an equation, I would actually find all solutions. If you're not specifically told to find all solutions in the interval 0 to 2 pi. So to find all real numbers that satisfy this equation, we have cosine of 3x equals negative 1/2. I'm going to start by doing a u substitution. Let's let u equal 3x here. And now I'm going to solve cosine of u equals negative 1/2. And where does this happen at? Where is the cosine negative? Well, the cosine is negative in quadrant 2 and quadrant 3. And so in quadrant 2, we'll have a solution. In quadrant 3, we'll have a solution for going from 0 to 2 pi. And we're finding the general solution. So we're going to say, well, let's see. I know that u then would equal 2 pi thirds. But allowing for all solutions, I would say plus 2 pi k. Or u would equal, right here would give us 4 pi thirds plus 2 pi k. And then we used u to simplify things a little bit, but remembering that u is equal to 3x, we actually are solving for 3x. So I'll write 3x equals 2 pi thirds plus 2 pi k, or 3x equals 4 pi thirds plus 2 pi k. And then for each of these equations, I'll multiply each side of the equation by 1/3. Okay, same thing. Okay, for our first equation, then we have x equals 2 pi over 9 plus 2 pi k over 3. The second equation, I have x equals 4 pi over 9. Whoops. Plus 2 pi k over 3. Okay, and we've got it. I'm just going to put the word or in between, and I'm going to say for any integer k. And I think somebody asked me the other day if we can use n instead of k. Sure, you can use any letter of the alphabet you like instead of k if you want, although probably here we wouldn't want to use x, right? Okay, so this would be our solution to this problem. And let's move on then to number 11. In number 11, we use the sum and difference identities to find the exact value of sine of pi over 12. And I'm just going to warn you, if it says use sum and difference identities, make sure that's how you solve this. If you would be told to use a half angle identity, which you could definitely do here, use a half angle identity because you'll get answers that look a little bit different using those two different methods. Okay, so if we're using the sum and difference identities, I would write sine of pi over 12 as being equal to, and you might have to mess with this a little bit to get the right breakup on the pi over 12, but I would use 4 pi over 12 minus 3 pi over 12, and there's usually more than one way you can go with this. There's not only one way to break up the pi over 12. So we would then write this as sine of pi thirds minus pi fourths. The reason we're doing this is I know what pi thirds sine is, I know what pi fourths sine and cosine for both of these are as well. And then we'll use our difference identity for the sine to write this as sine of pi thirds. Remember, the sine is the sharing function. It shares this first position with the cosine. So sine pi thirds, cosine pi fourths, minus, the sine gets to keep its minus, and then we have cosine of pi thirds, sine of pi fourths. Okay, and we should know what all those are. The sine of pi thirds is square root of 3 over 2. The cosine of pi fourths, square root of 2 over 2. The cosine of pi thirds is 1/2. The sine of pi fourths is square root of 2 over 2. And so we end up with square root of 6 over 4 minus square root of 2 over 4. We can write that as the one fraction, square root of 6 minus square root of 2 all over 4. Okay, and we have it. Then in number 12, we're given that the tangent is equal to -4/3, where theta is in quadrant 4, and we're asked to find the sine of theta over 2. So where I would start with this one is the very first thing I do is write sine of theta over 2. I'd write the formula, which hopefully you remember, plus or minus the square root of 1 minus cosine theta over 2. So there's a couple different things we need to figure out. We need to figure out whether we want plus or minus. So let's start there. Okay, so whether we use plus or minus, we're told that theta is in quadrant 4. Theta being in quadrant 4 tells me that 3 pi halves is less than theta is less than 2 pi. And then, but I'm not finding the sine of theta. I'm finding the sine of theta over 2. I need to figure out where theta over 2 is. So if I take 1/2 times 3 pi over 2 1/2 times theta, 1/2 times 2 pi. I'm just multiplying through by 1/2 here. I have 3 pi over 4 is less than theta over 2 is less than pi over, or is less than just pi, it looks like. Okay, less than pi. Okay, so what quadrant are we in? That's what we're interested in. We're in quadrant 3 pi 4 is less than theta over 2 is less than pi. We're in quadrant 2 here. Being in quadrant 2, the sign is positive. So that's all we're going to do in this step. Just check the sign. And then we need to figure out what the cosine of theta is. Well, to find the cosine of theta, we have the tangent of theta is -4/3, where theta is in quadrant 4. So let's draw a little picture here. So we're in quadrant 4, and it looks like we're going to use a reference triangle to solve this one. So again, I don't really care so much if I get the dimensions as long as I number my sides correctly. So we have a little right triangle here in quadrant 4. And if the tangent is -4/3, tangent is opposite over adjacent. And oh, this works out nicely. It looks like we have a 3, 4, 5 triangle again. Be careful on that though. This only works if your hypotenuse is length 5. If we had like this side was length 3, this side was length 5, we would not have a 3, 4, 5 triangle. So just make sure that it's your two shorter sides are the lengths 3 and 4 here. Okay, but this takes care of our issue here. We're trying to find the cosine of theta. So the cosine of theta, looking at our little right triangle here, we're in quadrant 4 where the cosine is positive, and the cosine of theta then would be adjacent over hypotenuse, which would be 3 over 5. Okay, so we can use that 3/5 to go back and finish our solution. We have square root of 1 minus the cosine of theta, which is 3/5 over 2. And now I'm going to use a trick that I like to use to simplify here. I'm going to multiply by the least common denominator of, and all we have is one denominator here within our fraction of 5. So I'm going to multiply by 5 over 5 underneath this fraction bar, underneath this square root sign. Sorry about that. And so we're going to end up with distributing 5 through to the 1. We'd have square root of 5 minus 5 times 3/5 is 3 over 5 times 2 is 10. We end up with square root of 2 over 10, which we'll work on simplifying here, is the same as square root of 1 over 5. That would be square root of 1 over square root 5, or just 1 over square root 5. So you can write your solution like this, and if we rationalize the denominator here, we'd multiply by square root 5 over square root 5, and we'd end up with square root of 5 over 5, which is another solution. Again, I don't care if you rationalize your denominator, but you're certainly welcome to do so if you like. Okay, and we'll move on then. Okay, so now we have an application problem. Suppose a 13-foot ladder leans against the side of a house, reaching to the bottom of a second floor window 12 feet above the ground. Let's sketch what this situation is. So we have a 13-foot ladder leaning against the side of a house. We'll say this is the ground. And it's always good to draw a picture on these. It will help you. It will prevent you from making a serious error that could get you the wrong solution. So we have 13-foot ladder and leaning against the side of the house, a second floor window 12 feet above the ground. And we're asked to find what angle does the ladder make with the house. So we're actually looking for this angle right here between the ladder and the house. I would tend to go for this angle on the ground if I didn't read the problem carefully. So it's a good thing to read and to draw a picture so you know exactly what's going on. And now to find what angle that is, well, we can just look at our picture, and I have an angle. I know the adjacent side, and I know the hypotenuse of this right triangle. And so for adjacent and hypotenuse, that tells me I want to use the cosine function. And I actually always write out cosine of theta equals 12 over 13. I write this before turning it into an inverse function or an inverse equation. And when I do turn it into an inverse to solve for theta, I have theta equals the cosine inverse or the arccosine of 12 over 13. And we plug that into our graphing, or not our graphing calculator. We use a non-graphing calculator in here. We plug it into our calculator, and let's see what we get there. I worked this out earlier. So theta is approximately equal. To be really careful to round where you should round to. In this case, it would be the nearest tenth, which is 22.6 degrees. Okay, so this is our angle that the ladder makes with the house, 22.6 degrees. Okay, let's go ahead and look at number 14 here. We're solving an equation. We have cosine of 2x equals 2 minus 5 cosine x. We're solving on the interval from 0 to 2 pi. So the first thing I would do is, well, we have two different choices here. But I would probably go ahead and write cosine of 2x in a different way. And we have like three different choices there for the cosine 2x. If I'm seeing only a cosine in the problem other than this cosine of 2x, I'm probably going to want to change this into the version of the formula that uses strictly cosines. And so I would rewrite cosine of 2x as 2 cosine x minus 1, and then on the right hand side of our equation we have 2 minus 5 cosine x. Okay, that on I forgot cosine squared x. 2 cosine squared x minus 1 equals 2 minus 5 cosine x. Okay, what you're going to want to do almost on all of these equations that you're solving is to get a 0 on the right hand side. So we have 2 cosine squared x. I'm going to add 5 cosine x to both sides to give me 2 cosine squared x plus 5 cosine x. And then if I subtract 2 from both sides, I have minus 3 equals 0. From this point, we'll try to factor our expression on the left side into 2 cosine x something, cosine x something. And I'll just kind of look at where we have a 3 and a 1. We probably want to multiply together. If I want a 5 here in the middle, I'm probably going to do a 3 and a 1 like so. And 5 in the middle is positive. So let's do plus, minus, and see if this works. So then if I FOIL together 2 cosine x minus 1 times cosine x plus 3, I get 2 cosine squared x plus 6x minus 1x gives me plus 5 cosine x in the middle, and then minus 3, it works. If we set then each of these factors equal to 0 to find our possible solutions here, I get 2 cosine x equals 1, or cosine x equals 1/2, and I get cosine x equals -3. So we're solving on the interval from 0 to 2 pi. So where is the cosine equal to 1/2 on that interval from 0 to 2 pi? The cosine is positive in quadrant 1 and quadrant 4. And so that's going to give me an angle of pi thirds in quadrant 1. It's going to give me an angle of 5 pi thirds in quadrant 4. And what about cosine of x equals -3? There's actually no solution here because the cosine is always between -1 and 1. It's never going to be -3. So we only have two solutions here, pi thirds and 5 pi thirds for our x values. Okay, let's go on to number 15, where we have 2 secant squared x equals 3 minus tangent x, and we're solving this equation on the interval from 0 to 2 pi. Well, the first thing I'm seeing is I have a secant and I have a tangent. Let's see what we can do about turning that secant into tangents. If you remember, if we think back to the basic Pythagorean identities, sine squared x plus cosine squared x equals 1. If I divide through by the cosine squared, then I have tangent squared x plus 1 equals secant squared x. And my goal here is to take this equation, 2 secant squared x equals 3 minus tangent x, and replace that secant squared with something involving tangent. Well, I got it, it looks like. So I'm going to just replace secant squared of x with tangent squared x plus 1. And let's simplify. We have 2 tangent squared x plus 2 equals 3 minus tangent of x. And bringing everything over to the left side so that we get a 0 on the right side. 2 tangent squared x plus tangent of x. And it looks like minus 1 equals 0. And like we did in the last problem, let's see if we can factor this. So this factors into 2 tangent of x. This is how I usually factor these. I kind of write out what I know I've got to have a 1 here and a 1 here. We just need to figure out where the minus goes. And if we want a plus in the middle, we probably want a plus here and a minus here. And let's check. If we multiply 2 tangent x minus 1 times tangent x plus 1, we get 2 tangent squared x plus 2 tangent x minus 1 tangent x minus 1, and this works. Okay, so now setting each factor equal to 0. And I think I may need more space for this one. Okay, I'm going to change colors and kind of bring this back over here. Okay, so if we set each factor equal to 0, setting 2 tangent x minus 1 equal to 0 will result in tangent of x equals 1/2. Setting tangent x plus 1 equal to 0, we get tangent x equals -1. Okay. So where is tangent x equal to 1/2 at? Let's see. So where tangent x equals 1/2, we're in the interval from 0 to 2 pi. Oh, let's sketch a little picture here. So the tangent is positive in quadrant 1. So some angle in quadrant 1 gives a tangent of 1/2. This isn't an angle that we know, right? And then the tangent is also positive in quadrant 3. So somewhere in quadrant 3, we should have a solution. So in quadrant 1, the only solution I can get actually is if tangent x equals 1/2, that tells me that x is going to equal the arctan of 1/2, or the inverse tangent of 1/2. So in quadrant 1, I have a solution of arctan of 1/2. But what about quadrant 3? Well, what we're going to do is we're going to have a reference angle in quadrant 3 of the arctan of 1/2. So what does that make our angle? Well, let's see. Our angle is going to be right here. And to find this angle, we could actually, I'm going to say, so x equals arctangent of 1/2, or x equals, we could take pi plus arctangent of 1/2. And we've got it. So these are the two solutions we get from 0 to 2 pi, where tangent of x is equal to 1/2. But let's go to our other equation we have here. Where is the tangent equal to -1? So the tangent is equal to -1. The tangent is negative in quadrants 2 and quadrants 4. And the tangent is equal to -1 in quadrant 2, where we would have a reference angle of pi 4. So we'd have x equals 3 pi over 4. Or in quadrant 4, we would again have a reference angle of pi 4. So that would give us an angle of 7 pi over 4. Okay, so x equals 3 pi over 4, 7 pi over 4, arctan of 1/2, or pi plus arctan of 1/2. All right, let's go on. Number 16, and I think this is the last problem that we have today. We're going to solve the equation sine of 3x cosine of x equals cosine of 3x sine x on the interval from 0 to 2 pi. Let's start by getting a 0 for this equation on the right side. And so I'll rewrite the equation as sine of 3x times cosine of 3x times cosine of x, and then we'd have minus cosine of 3x times sine of x equals 0. Okay, well this looks kind of like an alpha beta problem now that we're here. And if I think of this, if I set alpha equal to 3x and beta equal to x, then if you look at this, we have sine alpha cosine beta minus cosine alpha sine beta. Well, this sure looks like the sine of alpha minus beta, and we can solve the problem that way. We then have the sine of 3x minus x equals 0, which tells me then that the sine of 2x equals 0. Okay, and we could do a u substitution here if we want to. We could let u equal 2x, and that means that the sine of u equals 0. Where does that happen? If you think of on our xy coordinate system or the unit circle, where is the sine equal to 0? What that actually happens on the unit circle at 0 and at pi. So we have u equals 0 or u equals pi. Okay, but u is actually equal, okay, I am just doing an interval from 0 to 2 pi. The thing is, when our argument here is not simply x, we need to do a little more work. So I'm going to actually say u equals 0. We could say u equals 0 plus 2 pi k, or u equals pi plus 2 pi k. But we could do this even simpler, because notice going from 0 to pi, I just add 0 plus pi. Going from pi back to 2 pi, I just add pi again. So I could actually combine these two to write this as u equals 0 plus pi k, or just u equals pi k. Okay, so if we combine these to write u equals pi k, now we still have to solve for x though, so we've got u taken care of. To solve for x, what we're really saying here is 2x equals pi k, and that tells me that if I multiply both sides by 1/2 here, that would give me x equals pi k over 2. Okay, and now our general solution would be x equals pi k over 2 for any integer k. We aren't asked for the general solution here, but if we did find it, that's where it would be. The trick on when we're trying to solve sine of 2x equals 0 is we do basically have to find the general solution before we find the specific solutions. And if you remember in class, what we do here then is we'd make a chart of values for k, and for x equals pi k over 2. Technically, we should probably start with -1. But if we put -1 in for k, we'd have negative pi halves. That's not between 0 and 2 pi, so we'll ignore that. We'll go on, we'll put in 0 for k, and then x equals 0. If we put 1 in for k, we're going to have x equals pi times 1 over 2, or pi halves. If we put 2 in for k, we'd have x equals pi times 2 over 2, or just pi. If we put 3 in for k, we'd have x equals 3 pi halves. And if we put 4 in for k, we'd have x equals 2 pi. 2 pi. We can't include 2 pi. We cannot include it because there's an open bracket here. So our only solutions here then would be x equals 0, pi halves, pi, or 3 pi over 2. Okay, and we have it. And this is the end of this review. So my suggestion is to make sure that you work through the worksheets provided in your Canvas modules, work through the worksheets, work through the final exam problems that are listed there that would coordinate with the chapters that you've studied for this exam. And let me know if you have any questions, and I wish you good luck on this exam.